Welcome back. In this session, let's look at our core definition. All right, actually just another summary slide that discusses the definitions of population covariance of XY and sample covariance of XY. And as we saw in the previous session, the difference is in the averaging, just to first of all adjust for biasness, and also because of the same reasoning, it ends up being symmetrical or looking alike as the variance formula for sample variance. So uh, but the concept is the same. We want to find the average of the areas induced by each data point xi comma yi, all right, and the area of the rectangle is induced from the x deviation from the mean of x and y deviation from the mean of y. Right? So this is for population because we know mu x and mu y. And then we can do this for sample, and this is very useful because most of our data points measurements from in real life will be sample oriented, and we wouldn't be able to tell the population mean. So this is very useful here. So once we define this, we get covariance. And if I may just switch back to the hand-drawn figure, all right, so this is it, right? And at times, we define this guy here as SSXY. All right, so if you allow us to define that way, then we can then rewrite this covariance for sample as 1 over n minus 1 of SSXY. And that's just a shorthand, but it's kind of incredibly useful because then it allows us to see the whole structure very clearly. And of course, we need to remember SSXY is this. Now, we don't do that for population because SSXY, capital SS, right, that is basically talking about sample calculation. So we don't do that for population calculations because when we operate on populations, it's mostly theoretical. We use our theoretical findings to help us calculate and gain more insight in our sample measurements and calculations. Remember, sampling is where we touch real life. Population is where we are guided by the mathematics, assuming we have the capability to touch and measure every point possible, right? Now and in future and in the past. Now, of course, by saying that, it literally means always impossible, right? But that's the kind of marriage of the best parts between theory and practice, and that is theory guides us with a kind of complete understanding based on very ideal assumptions. But in real life, we never have ideal assumptions, right? So we at least know the limitations. We at least know what to expect when we are performing sampling. So that is the beauty of these two discussions between population and sample. So let's look at our sample, our slide here again. At the same time, we define correlation, and now we understand why we need to first understand covariance very clearly in depth first before we move on to correlation, because correlation is defined in terms of covariance. So we have the covariance, and then we divide by the standard deviation of x and the standard deviation of y. Okay, so there are also two versions of correlation, population and sample. And of course, we'll use consistently in both the numerator and denominators, population and sample versions. So if we're defining the population correlation, obviously we don't do population covariance divided by sample standard deviation. We don't do that, right? So we just be consistent. Population covariance divided by population standard deviation of x and of y. Correlation of sample correlation of x and y, covariance sample of x and y divided by sample standard deviation of x times sample standard deviation of y, and where we denote as Sx and x as 1. So these are the definitions. Now, why do we need correlation? Covariance itself is already very proper, correct, and objective in telling us whether it is a line or not, and whether it's positive line, negative line, and how line is this line, right? How linear is this line? The strength of linearity. So very nice. Why do we need correlation? Well, if you're thinking about let's say airlines, right? Okay, so we wonder, is it if x is the number of points being used to change certain free flight tickets, and then we go and find out about the market price of the market price equivalent of our free flight ticket. So then the market price equivalent will be measured in dollars, and the points we use will be just, let's say, points. It's unitless, but let's say it's points. So when you multiply the two together, that means the rectangle will have a unit of points dollars, right? And if you take the average, it is still points dollars, which is very hard to understand whether it is a large point dollar measurement or a small point dollar measurement, right? We don't have a feel about it. So that is the birth of, or rather the motivation for the birth of correlation. So correlation essentially is like covariance, except there is another standardization of the units. Yeah, so that when you have a covariance of 100, you can't tell whether it's very strong linearity or weak but positive linearity. You can't tell. Is 100 a lot or very little? We have no idea, because in point dollar form, we have no idea. But when you divide by the standard deviation, the standard deviation of x is going to be points, right? It follows units of x. And the standard deviation of y will be in dollars, because it will follow the measurements of y. And so you notice that the point dollar and the point dollar will cancel out, giving us a correlation that is unitless and standardized. These are the very important features of correlation, no matter what x and what y you use. And in this very kind of a sort of a extreme example, right? I mean, it's not really impossible. If we are trying to study how worthy is our mileage points gathered from flying, right? Frequent flyer points, right? So points dollar equivalent. When we calculate the covariance, it can't give us any inference except the plus and the minus. But we also don't know, because 100 may be very little. And for that matter, 1,000 might be very little. We have no idea, right? So, and if it's not dollars, if it's measured in yen, for example, Japanese yen, or some other currencies that are not having, cents, it's going to be a large number, right? So we lose the feel of how large or how small the covariance is. And that's very irritating. Yeah. So correlation really, really removes that problem. No matter what x units you use, what y units you use, right? So whether you measure the worth in Singapore cents rather than dollars, or you measure the worth in Vietnamese dong or Japanese yen, yeah, where there is no cents, it will still cancel out everything. So that if it's really a strong line with positive gradient, correlation will be very close to +1. It will never exceed +1. So that's nice. No matter what x and y you mix, it will never exceed +1. And likewise, it will never exceed, on the other end, -1, which is very nice. So it will be always definitively range bounded between -1 to 1, where +1 means very strong positive line with positive gradient, and -1 means strong linearity but with negative gradient, and 0 means points all over the place, no line perceivable. So that's nice and very practical, and that is the reason why we need correlation as much as we need covariance in theoretical exploration, because it's so easy and symmetrical to compute, right? So nice and well defined. We need correlation to be practical about reporting to humans, for humans to assess. After all, statistics is about communicating, right? Data to human. And so if it cannot inform us well enough to make proper action or decision, then a lot of the benefits will be lost, right? So thankfully we have correlation. Just to wrap up the discussion on the symbols and definitions, we also use R. So R is basically the symbol, because remember it's alphabet, it's not Greek letter, so it's sample correlation. And if you look at the definitions, the 1 over n minus 1 and the 1 over square root n minus 1 and 1 over square root n minus 1 in the Sx and Sy, they will cancel out and result in having SSXY. Remember what's SSXY? Which is this guy here, right? Only the sum, no division, only the sum of the products of the areas, of the lengths. So SSXY and SSXX will just mean that the y is replaced by x. So you have xi minus x bar squared. That's SSXX. And SSYY, you replace the x by y, and that's all. So let's just look at the slide again. And that's why we end up having this, right? So it's not to say covariance sample is now being changed to SSXY. It's to say that when covariance sample is divided by SX and SY, the 1 over n minus 1 here and the 1 over square root n minus 1 from Sx and 1 over square root n minus 1 from Sy, they cancel out. So this only makes sense when you put it in this ratio form, all right? Okay, so that's one point. Second point is, of course, we don't forget our symbol for our Greek symbol for the population version of correlation, right? So that's rho here. That's not P, that's rho, RHO. And in a similar fashion, it's defined as sigma of xy. Sigma of xy is basically this guy over here, just this guy without dividing by n. So that's our sigma for xy. And it's quite easy to see why it's a very handy symbol to do that, right? So rather than plonk in a huge summation, and we know what is standard deviation, population standard deviation for x, and that for y. Okay, so SSXY, yeah, we have it here as a reminder, and sigma xy here as a reminder. Okay, great. Now, do we have alphabet and a Greek letter for the covariance? Well, in short, no. Not commonly used, not commonly seen. I don't find it anywhere. So if you find anything used, you can let me know, but it's not a commonly used symbol. So stick with covariance, just COV, right? And this suffix symbol, suffix sample, is what I put in here to differentiate my intention of usage. So when there is no suffix, it always refers to population. That means both x and y are populations. Remember, random variables can represent either population or sample. So if our covariance here doesn't have a suffix, then it is implied that x and y both represent populations. And if there is a sample suffix here, then that means x and y are random variables that represent samples.